Okay, a couple other special cases I want to talk about would be if you have trinomials. So kind of going back to the ones that we saw when we were using our shortcut, but also the ones where we were having to group. Sometimes we have cases that are, again, special cases based on kind of the numbers that you're working with. So a couple things that you want to check when you have a trinomial is that you want the first and the last terms to be perfect squares. So again, you want to think about those numbers that we've talked about before. You can't have negatives. So the first term and the last term have to be positive, okay? And then the middle term can be positive or negative, but it has to do something specific. So whatever the A and the C are, those are your perfect square numbers. You're going to want to square root them, and then you're going to want to take those individual numbers times 2. So it kind of is going to double again in the middle. And similar to like when we did our shortcut when we were multiplying these types of things, these would be the cases where you had like x plus 2 squared. And we talked about that the shortcut for multiplying is that you square the first term, you square the second term, and then the middle term is you multiply them together and you double it. So that's kind of where we're going with this rule, but we're factoring it now. So we're kind of undoing the multiplication. So the first examples here are asking, are these perfect square trinomials? And if they are, factor them, okay? If they're not going to work for these 3 rules, then you're not going to be able to factor it, okay? And again, you can write not factorable, or another answer that would be acceptable is you could write prime. So even back up on here on this one where it said not factorable, if you wrote prime, that also means the same thing. Like I can't factor it based on what they're giving me. Okay, so let's take a look at these examples. Down here, first thing is I'm going to check is my first and last terms perfect squares. So can I square root the x squared and can I square root 64? Well, the square root of x squared would just be x and the square root of 64 would be 8. So yes, that takes care of rule number 1. Rule number 2, their signs cannot be negative. Both of them are positive, so I don't need to worry about that. Step number 3 is does this middle term do where I have these 2 terms, x and 8, and I double it. So 2 times 8x would be 16x, and that is what they have in the middle. It's okay that there's a minus sign here. That tells me that when I go to factor it, I'm going to grab the x and the 8. This whole quantity is going to be squared, and this minus sign that's up here is going to be the sign that goes in between those 2 terms. So let's say that this was x squared plus 16x, then instead it would say x plus 8. Okay, so let me just give you another example over here. Let's say it was x squared plus 14x plus 49. I would square root the first and the last. That'd be x and 7. And then if I take 2 times 7x, that is 14x. And so this one would come out to be x this time plus 7 squared. So you can kind of see that sign only impacts what's going to go in that factored answer for your parentheses. Okay, if you look at the next example here, if you square root the 36, x squared, that's a 6x. The square root of 16 would be what? 4. And then you check the middle term. If I take 2 times 6x times 4, so that'd be 2 times 24x. That should come out to be 48x. Is that what they have in the middle? No. Okay, so this one does not follow the rules that I had up above, so I can't factor this, so I'm going to say it's prime. Or you could write not factorable. All right, so those are some special cases with the squaring, like anytime you have an x squared. So we kind of talked about the difference of 2 squares, and then we also talked about those perfect square trinomials. Now let's talk about another special case, and this is when we get into exponents that are 3s. So the difference or the sum of 2 cubes which would be kind of similar to what we did with the difference of squares, but instead of perfect square numbers, we're looking for perfect cube numbers. And we've also talked about perfect cube numbers. Remember, those would be like 2 to the third is an 8, 3 to the third is 27, 4 to the third is 64. So we listed those numbers out earlier in our notes as well. Those numbers start to get really big really fast. But again, those would be numbers to look back on to see if they can be cubed or not, cube rooted or not. We have two rules for cubes. We have the sum and we have the difference. There's a typo here. This should be difference, not another word of sum. So I'm just going to squeeze that in there. But so when you have two perfect cubes that are being added together and you want to factor it out, you can use this top rule. Where the a and the b come from is when you cube root the terms that you're working with. So if you had like a 27 x to the third, the cube root of that would be 3x, and that would be like your a term or your b term, depending on where it was at in your problem. And then you just kind of plug it in the respective places there. The same thing works with the subtraction rule. It's just some of your signs are different, and they're really subtle differences here. So you can see like this one starts a plus b, this one starts a minus b. And that kind of just comes from the sign that you're starting with, whether it's sum or difference. But then all the letters look the same, but for the sum, you have a minus sign first and then a plus sign. For the difference, you just have two plus signs. Okay, so find a way that makes sense for you guys to remember that. Even if it's just repeating it to yourself multiple times or trying to just find a way that maybe helps it stick for you so that when you're dealing with factoring later, you kind of know which sign I should have. Okay, so here's an example. If I had 125x to the third minus 8, okay, these are two perfect cube numbers, okay, because like the cubed root of 125 would be 5. And the cube root of 8 would be 2. All right. And then this would also have an x attached to it because that x to the third would also go underneath that cube root sign. But that would be the first thing that I would do is figure out what is like my a and my b. So this 5x is going to be your a term and this 2 is going to be your b term. Okay. And you can see how they rewrote it like that in those parentheses. And they're just putting that minus sign in there because that was what was in between the terms. Then if we follow this rule that they have written out up here, in the first set of parentheses, you do your a minus b, so 5x minus the 2. And then you square the a term, which is the 5x. So you see how they have 5x squared. And then the middle term is your a times your b, so just the 5x times the 2. So that's kind of getting me to here. And then the last term is just your b squared, which is the 2 squared. And the last thing that you should just be able to do is kind of clean it up a little bit. If there's any numbers that you can operate with, that's just what they're going to want to see you do. You can't really do anything with the first set. It just stays 5x minus 2. But 5x squared becomes 25x squared. 5x times 2 becomes this 10x. And then 2 squared becomes 4. And so that just kind of cleans it up a little bit more. Okay, why don't you guys go ahead and try this one, 64x to the third plus 27. Okay, so the first thing I would do is cube root both of your terms. So this becomes 4x, and this is a 3. And then instead of using the subtraction rule like I have up above, I'm going to use the sum rule, which is very similar. So you're going to take your first two terms, 4x, and it's going to be plus 3 this time. Then you're going to square the 4x squared. There's going to be a minus sign here, and then 4x times the 3, and then you're going to square the 3. Okay, and then it should clean up to 4x plus 3, 16x squared minus 12x plus 9. Okay, so I've gone through a lot of different cases here today. And so I kind of just have a general strategy. These are just things to maybe think about when you're going to do one on your own. Because I think the hardest part is differentiating when do I use each method? When do I use the shortcuts? When do I need to use grouping? When can I just factor it by using like my little table charts that we were doing earlier? So here's what I would do. The first thing I would check for is look at your terms. Look at how many terms you have. Is there anything that you can take out of everything? So is there a GCF that maybe we can divide all the terms by 2, or can we take an X out of everything? Okay. Then if there's nothing that you can just pull out and just use your GCF method, figure out how many terms there are in your polynomial. Okay, if there's only 2 terms, chances are pretty high that you're going to be using the difference of squares or the sum or difference of cubes, because those are the problems that only had 2 individual terms. So for example, if you had like x squared minus 16, or you had x to the third plus 27, those would be those kind of cases where you have 2 terms to them, and you'd maybe be using one of those shortcuts. If you have 3 terms, if it's a perfect square trinomial, okay, so like the one that we saw earlier said x squared minus 16x plus 64, where you kind of check those rules. You know, do you have perfect squares at the beginning and the end? If you square root those and double it, is that the middle term? Okay, then you can use that shortcut pattern. If that doesn't happen, and you have the ax squared plus bx plus c, you can use your grouping method, you know, where you have to take your a times your c and rewrite it and then drop those parentheses in to factor it off. If it's an x squared, so there isn't a number in front of the a, but it doesn't fall underneath the perfect square because you're not necessarily dealing with perfect square numbers, then you can still use those shortcuts that we talked about, but you're just kind of thinking, you're thinking about the table, okay? The last thing would be trial and error, and I know that that's not really always helpful, but sometimes you might just have to kind of try and see what happens. And if you can't get it to work, or you've tried multiple approaches to it, it is possible that you might have stuff that just can't be factored. Okay, if you have 4 terms or even more than that, you're probably going to be grouping. Okay, because there's really no shortcut for those. There's really no way to just do a simple table and like figure it out. You're going to have to drop those parentheses in there, start looking for your GCF. Okay, I've got one more problem here, and this one is just kind of taking our factoring methods that we've been talking about, but also applying those exponents that we've seen in the past where they're fractions, and kind of how we deal with this. So on this one here, I'm noticing that both of my pieces have this x minus 1 raised to the negative 1/2 power. So I'm going to start by using my GCF method, and I'm going to take out what's in the front, which is an x, and then what number's here? There's a 1 there, right? So make sure that you're going to pull out x plus 1, and then they both have this x minus 1 raised to the negative 1/2 power. Okay, now let's think about what that really is. We can't have negative exponents. So I would rewrite this. I would leave that x plus 1 on top, but on the bottom it's going to say x minus 1 now to the 1/2 power, because when you move it to the denominator, it gets rid of the negative exponent. But think about what we've talked about in the past. What is really happening to the bottom there when it's raised to a 1/2 power? It's technically a square root. So it's the square root of x plus 1, or sorry, x minus 1. Okay? But remember, we can't leave a square root in the bottom like that. So we have to multiply by its conjugate. So remember what we're going to do is multiply the top and the bottom by the square root of x plus 1. Okay, so when we do that on the top, I can't really do anything with these because one's not in a square root and one is, so I'm just going to put them side by side. And then I want you to see what's going to happen on the bottom. So I'm going to do this kind of underneath it here. Both of these things are underneath square root signs, which means that I can multiply the terms together that are underneath them. And I'm going to do that by foiling. So my first term would be x times x, which is an x squared. The outside would be x and a negative 1, which would just be a negative 1x or negative x. The inside term does the same thing, negative x. And then negative 1 times negative 1 would be positive 1. And so if we take this a step further, it looks like this, which kind of, I want you to think about this. If I were to factor, it would go right back up to x minus 1, because it's one of those shortcuts that we talked about. And so really what's going to happen is because you have the same square root here 2 times, we've talked about this before. If you have like the square root of x times the square root of x, or the square root of 5 times the square root of 5, we talked about how the piece on the inside is just going to pop out. So I'm showing you how this x minus 1 is going to eventually just come out of here. And then there's no more square root. And this is going to be your final answer.